Quarter past, I think we are good. Well, thanks for coming. Well, we keep increasing the number, and maybe because we have a popular speaker here, but we are very glad to have Ville Hyvönen here with us. And Ville is a PhD researcher, currently working with the Teemu Roos group. And they're going to present this work that was actually accepted and also going to present at the New IPS this year. So congratulations again.
Thanks.
And I'll let you speak and present this work. Very interesting. Thanks.
Okay, thank you. Hi, everyone. Thanks for your interest. The topic of today's talk is multi-level classification framework for approximate nearest neighbor search. And this is based on joint work with Elias Jaasaari from Carnegie Mellon University and Professor Teemu Roos, who is my supervisor. And this article will also form the backbone of my PhD thesis. Okay, so a little bit background. The problem we are working on is approximate nearest neighbor search, ANN. I will use the shorthand ANN in this talk. And the simple or the exact KNN search or K nearest neighbor search, the task is to find K nearest neighbors for the query point from the fixed database. And this fixed database or this fixed dataset we call corpus. So in this simple toy example, you can see this corpus point are in green, and the query point is the yellow star, and in this example, K is 5, so the 5 nearest neighbors are highlighted in orange. So we will use this simple toy dataset as an illustration for the rest of this talk. And because in many modern applications, the datasets, they are very large and high dimensional. So very often this problem is relaxed so that the approximate solution is allowed. So for example, we can have some recommendation system, and the data points, they are the items in the inventory. They are represented as points in some high dimensional vector space. And the query point will be this, let's say it can be an item the user is browsing, and it is also converted to the item in the same vector space. And of course, then the inventory is usually very large, and the representation is usually high dimensional, hundreds or even thousands dimensions. And in this case, because it's a real-time application, also the fast response times are required, so that's why the approximate search is often used. So this is the motivation of this problem. And in this work, we focus on the partition-based approximate nearest neighbor algorithms. So in these partition-based algorithms, we learn a partition of the feature space. And in this example, you can see, in this 2D example, you can see the partition is marked in blue. And to give a concrete example, this partition can be learned in either flat or in a recursive fashion. And the flat partitions, they are called hashing-based algorithms, like the local-sensitive hashing, shorthand LSH. This is the most well-known of these approaches. And it's the indices, they are called hash tables, but this is like a little bit computer science. In mathematics or in machine learning, we can just see that they are actually partitions of the feature space. So this is maybe a simple way to approach them. And the recursive partitions, they are called space partitioning trees. And they are usually learned in unsupervised fashion. So the feature space is partitioned in a recursive fashion by using the corpus as a training set. And I will give a little bit or a couple of concrete examples of these space partitioning trees. So in a random projection tree, the data is first the random direction is chosen from the d-dimensional normal distribution, or the equivalently from the surface of the d-dimensional unit sphere. Oh, this is my supervisor, Professor Teemu Roos. And then the data is projected onto this random direction, and it is split at the median in this projected direction. So this is actual example I have generated this. So these are all the partitions are all real. And another traditional method, this is maybe the first and the most well-known index structure for ANN search is KD3. And in KD3, we actually use the highest variance direction, or highest variance coordinate direction. So in this tree, the splits are restricted to the direction of the coordinate axis. So at each node, we see in which direction the data has highest variance, and then split at this direction, at median at this direction. And the third variant is the principal component, or PCA3. This is like the KD3, but the splits are not restricted to the direction of the coordinate axis. So we can pick the highest variance direction in any direction. Okay, so now to how these partitions or space partitioning trees, how they are traditionally used for approximate nearest neighbor search. So this is what we call the lookup search or lookup-based search in our work, but this is basically this is how it has been done before. So the query consists of two steps. First, we look at which points belong to the same partition element as the query point. So here in this partition element, so we will look at which scopus point belong into it, and then do the exact search among these scopus points in this partition, inside this partition element. So here you can see the candidate set points are highlighted in yellow. So you can see all this yellow point here, this is the candidate set, and then we do the brute force search in this candidate set. So here you can see how this makes the search faster, because we have a much smaller set of points where we have to do this brute force search. But of course, the problem is then we can miss some of the true nearest neighbors. So in this toy example, we would miss these two true nearest neighbors because they are outside of this partition element. And then there are some extra points which are not among the true nearest neighbors of the query point. So this is the traditional approach. And of course, this is, you can see, this is not super optimal way. And what is usually done is used multiple randomized partitions, and then a backtracking search where the multiple partitions are explored and all the results are aggregated. So if the point is in the same partition element in any of these partitions, they are chosen into the candidate set. Okay, and let's take a little bit step back. This is actually, now forget about this nearest neighbors and corpus. This is just this is the same toy data set, but this is just now the setting is just the normal binary classification. So what the point I want to make, how do we usually use partitions as classifiers in machine learning? How do you usually do it? Because we were not very happy with this traditional method I just presented to you. We felt like there was something missing, something wrong. So now we take a little bit step back and think about the traditional binary classification. So here, this is just the training set, which consists of two classes. So class 1 and class 0. So very traditional setting. And then when we have a partition, let's say this is, you can think it as a decision tree, just a normal decision tree. So what do we do now? If we want to classify this query point, we usually do just we can do the majority voting in this leaf or the partition element the query point belongs into. So there are 6 training set points in this leaf, and 4 of them are class 1 and 2 of them are of class 0. So the point will be classified to query point will be classified to class 1. And of course, if you want to get a little bit fancier and compute the probability estimates for these classes, then the probability estimate of the class is just the observed proportion of this class among the training set points of this cell the query point belongs into. So in this case, the probability estimate of the class 1 would be 2/3, and the probability estimate of the class 0 would be 1/3. Okay, so this is the traditional binary classification approach. And now to the research question that has been motivating our work. Can we actually do the same thing in this nearest neighbor search? Can we actually formulate it as a estimation or machine learning problem from the first principles? And okay, let's take a look how this might be done. Okay, so we just basically take a brute force approach and try to define all the things we need to define a machine learning problem. So first, the input variable, that's easy. That's the query point or the any point in this feature space. And okay, now this is maybe the crucial part, what is the output variable? So it is we have the scopus points. They are here numbered from 1 to 23. And we want to find the true nearest neighbors. So they are, of course, some of these or 5 of these scopus points here. So what we actually have here is the multi-level classification problem, where the classes or the labels are the scopus points, and the true labels of this query point are defined by its 5 nearest neighbors among the scopus. So for example, here we have the query point X, and its 5 nearest neighbors are here again. And so you can see the true label set is 5, 6, 7, 11, and 16, because the corresponding scopus points are the nearest neighbors of this query point. So this is basically the ground truth, or the true value of the output variable, or the true label set of the query point. And finally, what is the training set? This is maybe the only complicated part, or this is we actually hypothesize that this is why this has not been came up before, because the training set, it can be actually the corpus itself, unless we do have a sample from the actual query distribution. So in this case, we will use the corpus itself as the training set. So it will be used in a dual role. On the one hand, it defines the labels, the true values of the output variable, but on the one hand, it's also used as a training set. So if we use corpus as a training set, then we look at the nearest neighbors of the corpus points among the corpus points itself. So for example, here we have the 10 corpus points, and its nearest neighbors are of course, the point itself. So the 10 focus points and the focus points 9, 11, 12, and 14. So these are the 5 nearest neighbors of it. So these are its true labels. And of course, if we have a sample from the actual query distribution, then we can use it also as a training set. I will return to this point later. Okay, and now when we have a partition, how do we choose the training set using this partition in this multi-label classification framework? We just defined it as a basically standard multi-label problem. So how do we choose the candidate set? Okay, so this is, we basically do the same thing as in the binary classification case. We look at the we look at the training set points that are the same leaf, same partition element as the query point, and look at the tail labels, which correspond to the nearest neighbors. So this means that, for example, for this 8 focus point, its probability estimate is 4 out of 6, so 2/3, and this is because it belongs in the 5 nearest neighbors of these 4 points, including itself. So this is how we compute these probability estimates. So they are just the observed proportions, label proportions among the points in this leaf or the partition element. So here I have actually computed all the probability estimates for these training set points. So for example, this point here belongs to the 5 nearest neighbors of the only 1 point here, and it is actually this point here. And now we choose the candidate set. As in multi-label classification, normally we just pick all the labels that have the score function value or the probability estimate that is higher than given threshold. And in this toy example, we use the threshold tau is 0.2. So here I have highlighted in yellow all the points that are chosen into the candidate set. So unlike in the traditional lookup-based search, we don't automatically choose all the corpus points that belong to the same partition element as the query point. As you can see here, even though this point here belongs to the same partition element, it is not chosen in the candidate set. And on the other hand, this point here, it doesn't belong to this partition element, but it is still chosen into the candidate set. So we look at the nearest neighbors of the points that are in the same partition element as the query point, and look at their nearest neighbors, and then they define the probability estimates without a threshold to choose the candidate set. So this is our approach. Okay, and above, we assume that we have already learned a partition, so the partition was fixed. But we can actually use this machine learning approach to directly learn a partition. Because we have defined the candidate set selection as a multi-label classification problem, we can just train a standard multi-label random forest to solve this problem. And here we actually use the pick all labels problem reduction, so we don't need as many trees as there are classes, because there usually are millions or even billions of corpus points, so millions or billions of classes. So of course it would be very inconvenient and computationally heavy to build as many trees. so we can actually tackle all the classes using a single tree. Okay, and now of course, see, this is very, for us machine learning and statistics people, this is very constant and very satisfying way to define the problem. It brings us lots of joy to define it this way. But of course, you can ask if this is any useful. What are the implications for it, or is it purely academic? So I will go, there are basically three kinds of implications. I will start with the most obvious and maybe useful one, so the empirical results. So we actually compared to this, our candidate set selection method, the natural classifier that is directly suggested by this our framework. We compared it to this traditional method lookup search. And then there's also the third method, which is the variation of the lookup search. It's called voting. And it's, I just, in my demonstration, we used only one partition. But like in machine learning, usually you don't use only one decision tree, you use a multiple randomized trees that is called random forest. So here, we usually the same approach is used. So if multiple trees are used in voting, not all the points that are in the same partition element as the query point in any of the trees are chosen, but there's the tuning parameter, let's say it's 6. If the tuning parameter is 6, then only the points that are in the same partition element in at least 6 trees are chosen into the candidate set. So this is the variation of the lookup search, and we included it for completeness because it has actually better performance than the vanilla lookup search. And we used the three kind of trees I just presented you in the beginning. So KD, PCA, and RP trees. We used these trees and we combined it with all of these three candidate selection methods to see which one is the fastest. Of course, in approximate nearest neighbor search, there are basically two metrics which has to be combined. The one is recall, so which percentage of the true nearest neighbors are returned. So if the recall is 0.9, then the 90% of the true neighbors are in average returned. And of course, the recall is not sufficient because you could just do exact search and then get the 100% recall. So the another variable is query time. So how fast do you return the nearest neighbors or the approximate neighbors? And it's we measure the actual running time. So we have implemented everything in C++, and it's optimized and fast, and we measure the actual running times or the averages. So here are the results on the first dataset. So here you can see on the x-axis is the recall, and on the y-axis is the query time. So the lower the curve, the faster the query time for the given recall level. And here you can see the lookup search is in the red dashed dotted line. So it's the slowest on, here's the random projection tree, here's the KD tree, here's the PCR tree. So for all the three types, the vanilla lookup search is the slowest, and in the between is the voting search, and the natural classifier that is suggested our methods is the fastest. So it's faster than the existing candidate set selection methods. In this dataset is Fashion Amnist, and the order is same on the GIST, on the STL10, and on the Trevi datasets. So the results are very consistent. So this actually improves for all types of trees and all datasets. This machine learning approach actually improves the results, and it can be used in combination with any type of tree. So it seems, at least in our experiments, it works. Okay, and then we compared the different types of trees. The principal component trees, KD trees, and the random projection trees. And then we, as I mentioned before, we also trained a poorly supervised random forest because these three types of trees, they are unsupervised, but this random forest is actually supervised. So we actually use the real labels that correspond to the nearest neighbors. We use them to train this random forest. And here are the results. Our hypothesis was that the random forest will be fastest on all the datasets because it uses the supervised information. And on the first two datasets, Fashion and Gist, this is the case. But actually on the most highest dimensional datasets, the PCR trees are the fastest, not the random forest. And why this is so? This is only a hypothesis, but we think this may be because these are very high dimensional and they are not dimensionally reductive, these datasets. So in this, because the decision trees used by random forest, they are restricted to the direction of the coordinate axis, so they can use only one direction, but the PCR trees can actually, even though they are trained in unsupervised fashion, they can actually find oblique split directions that may be more informative than the single coordinate axis directions. Okay, and let's move on to the theory. We can actually consider since we have now a multi-level classification problem, we can actually consider it in a standard statistical learning framework. And of course, we are interested what happens when we increase the training set size, the standard asymptotics. But in the above, we use the corpus itself as a training set. But here, we will have a external training set, the sample from the actual query distribution. So here they are the pink points here. This is the actual training set. The corpus and the query point are same as before. Then we using the brute force search, we can find the true nearest neighbors of these training set points from the corpus, and then use this set training set. Okay, and here I've highlighted the least. It's actually, I forgot to mention, this is the PCR tree, so principal component tree now. I've highlighted the partition element the query point belongs into, and I have highlighted the training set points that belong into the partition element. Okay, and now the label probability estimates, they are actually defined by the nearest neighbors, not the nearest neighbors of these corpus points, but the nearest neighbors of these training set points. So here, for instance, for this, the probability estimate for this corpus point is 3 out of 6, so 1/2. I'm sorry, there actually, I think the one of the training set points here did not fit into the margin, so you got the only 5, but they're somewhere hidden. So it is among the 5 nearest neighbors of these 3 training set points, so that's why it's 3 out of 6, the probability estimate. And we choose the candidate set using the same technique as before, just threshold this probability estimate standard multi-level plugin approach. And so here you can see in this case the recall is 3 out of 5, since they are we found 3 out of the true 5 nearest neighbors of the query point. So these 3 are belong to the candidate set, these 2 do not belong. And the precision is 3 out of 7 because there are 7 points in the candidate set, and 3 of these 7 points are true nearest neighbors. Okay, and now what happens when we increase the training set size? Let's see. We keep the number of points in the leaf approximately constant. Okay, and this time you can see again the candidate set in yellow. And now actually all the true nearest neighbors are chosen into the candidate set. So the recall is perfect 5 out of 5. But now there are a little bit more points in the candidate set. There are 10 points in the candidate set. So the precision is 5 out of 10 because this 10-point candidate set contains 5 true nearest neighbors. And let's keep increasing the training set size. Now you can see the grid is more thick or narrow. And again, we find all the 5 out of 5 nearest neighbors. And now there are only 6 points in the candidate set. So this is the only point in the candidate set that doesn't belong into the true nearest neighbor. And of course, this example is not cherry-picked by the way. It's the first example I generated. But of course, this is stochastic process, so it can go down or up. But as we can see, and one more thing. Actually, now to contrast with the original lookup-based approach, where the corpus point has to belong to the same leaf as the query point, if it will be found. In this example, actually none of the true nearest neighbors belongs to the same partition element, and we still found every one of them. So this is to illustrate the difference of these two approaches. And okay, now probably you can see the intuition, or what will happen, or what we hope happens in the limit when we increase the training set size. The diameter or the size of these partition elements goes to 0 or is very small. And in this case, of course, all the training set points that belong to the same partition element as the query point would have the exactly same neighbors as the query point by the simpler geometric argument, because they are of course very near to the query point if it's very small, the partition element. So this is the intuition, and it turns out we can actually formalize this intuition. So basically we will show that this is actually the case. So if we have an external training set and the diameter of the partition element where the query point belongs into converges to 0 in probability, then this is actually consistent, this classifier for, okay, and a little bit technicality, it's for the multilabel 0-1 loss. So this just means that the precision recall are perfect, so that the candidate set contains only the correct labels and no other labels. So it returns exactly the perfect candidate set. And we can show that this is actually the case. And we assume that the query distribution is continuous. This is just the technicality. I think we could do without the assumption, but then we would have to take care of the pathological case where the data points will be the concentrated on the hyperplane that is exactly between two corpus points. So we assume continuity because of this technicality. And then we illustrate this result by verifying this condition for chronological KD trees, which is the first data structure that is actually suggested for nearest neighbor search. So we prove that for these trees, the diameter goes to 0 in probability when the training set size increases, and thus we can use the former results to prove the consistency. And okay, and finally, the last thing, the future research directions. Of course, there's always the theory. You could prove consistency of other data structures, but we actually find the research direction we find more interesting is the empirics, or the fact that we can use actually any classifier, any multilevel classifier as an index structure in this framework. So we used random forest but of course, traditionally, the gradient boosted trees perform better than the random forests, so it would be very interesting to actually try them and see how they work. Also, there are the extreme classification methods that are specifically meant for multi-label problems, where the label space is very large. So these are very promising. And of course, since the basic PCR trees work very well in high-dimensional data, this arises a question whether we could train the SVM type trees, where we'll actually use the hyperplane, like arbitrary hyperplane that is optimized in supervised fashion. So that is also one interesting research direction. Okay, and to conclude, we formulated approximate nearest neighbor search as a multi-level classification problem. And in this multi-level framework, the partitions are interpreted as multi-level classifiers. And this approach enabled us to improve the performance of any partition for approximate nearest neighbor search, and also use any multi-level classifier as an index structure. And finally, it enables us to consider asymptotics in standard statistical learning framework. And okay, thanks for your attention. And if you have any questions, now it's time to ask them. Yep.
Yeah. So interesting talk, thank you. I'd like to ask about so if you go back to the slide where you first showed the multi-label classification kind of formulation.
Here?
Yeah, sure. So here you mentioned that the training set for the classifier is the corpus.
Yep.
And then you define the labels as the true nearest neighbor, right? Or the indices for the true nearest neighbors.
Yep.
So why do you need the partitioning after this? Couldn't you just have the classifier output label indexes? So let's say you choose K to be 10, then you have the classifier output 10 numbers, which should be like an approximation to the.
Oh yeah, that's good question. A very good question. We actually tried that and it did not work. So it's the answer is simple. It's the basically the most elegant solution, but empirically it doesn't work very well. So empirically you get much better results if you pick larger candidates at, let's say, 100 or 200 points and then do the proof of search in this.
So you could output 200 labels and then do that.
Yeah, this is the pipeline.
Okay, but what are the partitions like? Because in this way you don't need the partition, right?
Oh yeah.
Well, I guess the partitions are defined by the classifier itself.
Can I ask a kind of a clarifying question?
Yep.
So, like, we can't just do a lookup because we will be facing queries that are not members of the corpus.
Oh yeah, that's the
that was the original answer. That.
Oh right. So yeah, thanks. Yeah, right. So this is the idea is to build first offline an index structure and then use it in some online system where you get new queries. So that's okay. Yeah, good question. Yep.
Do you assume that points are somehow uniformly distributed in density? So what happens to your algorithm if you have some areas where it's very dense, they have a lot of points, and then you have some areas which are very sparse? So in this case, I think a fixed K might cause some problems. So am I wrong?
Well, do you mean the?
So let's say that in this picture there was one point at the very left where there's no neighbors really around it. So
Yep.
You have a lot of variance in how dense the areas are. So how does what happens to your algorithm? Does it still work?
As far as we know, it still works because we use these usually space partitioning trees, so they are adaptive to the density. So if there's it always, because we use median splits, so they are always in each cell, they are always same amount of points. So it's the probability mass of the empirical distribution of the data is always the same. And of course, we actually use this fact in our proof. We have to use the Wapnick-Chervoninckis theorem, which states that the true distribution is close to the empirical distribution given there's enough data.
Okay.